Good afternoon, ladies and gentlemen, dear colleagues. Welcome to Science Lunch. This is a special event where science meets food, which is always fantastic. I hope you enjoyed your lunch. And now please take a seat and we will start with the scientific part. As usually, we have a speaker at Science Lunch. This time it will be Petr Hauschwitz from HiLASE, and he will talk about laser nanostructuring. Before we start, I still also like to announce another event that will take place just after this event, which is in the main lecture hall in the main building, and it's the science career from other perspectives. So for those who like to hear a little bit more about more personal view of how science is done and what it takes, please go afterwards and visit the other talks that will be the main lecture hall. Okay, so that's for the announcement. So and now it's my pleasure to invite Petr Hauschwitz, and we look forward to your talk.
Okay, thank you for a nice introduction. So my name is Petr Hauschwitz. I'm a team leader of laser micromachining at HiLASE Center, and today I will be talking about nanostructuring and surface functionalization with. So I guess I don't have to introduce you to HiLASE Center. But if you look into HiLASE structure, where is the micromachining team, you can find us in industrial laser application team, and we are one of three main applications there. Application teams. Here you can see my team. It's 3 postdocs and 2 undergraduate students, which are not shown here. So quite a small team. But now let's jump to laser micromachining, which you can imagine as precision cutting and drilling, but in micrometer dimensions. Here, because we have very nice tools, I will come to that. For such precise machining, we can process even some special alloys, glass, dielectrics, silicon wafers, and even composite materials with these dimensions. But except that, we are focused also on surface functionalization, which is a technique where we create a special kind of micro and nanostructures on the surface, which can change the surface properties. That means we can change just simply the visual, make the surface texture made or glossy, but we can also change the friction coefficient, or for example, wettability. We can make the surface superhydrophobic or superhydrophilic. We can also change cell adhesion, antibacterial properties, and so on. It's quite a broad range of applications which we can do with just different kind of micro and nanostructures. And of course, to make such detailed and delicate structures, we need a very precise tool. In our case, it is laser which is developed at HiLASE called Perla. I will not go into details, but let's say that the pulse duration enables us to induce minimal heat affected zone and thus reach very fine details. But also we have enough power to do this processing efficiently. And that's exactly one of our another advantages, that we are also trying to transfer this scientific discipline into industrial environment, because the current limits in laser micromachining are mostly speed of basically the cost, which is due to low processing speed and also due to inefficient use of laser power. I will give you an example here. If we think of common micromachining setup, which can move the beam with a speed of 1 meter per second, and we want to create such micropillars for superhydrophobic surface, then we will end up with something around 7 days per 1 square meter. It is already quite a long time, but if we look here and we would like to enhance this superhydrophobic effect by a second layer of nanostructures, then we will end up with 2.5 years per 1 square meter, and it is already unthinkable for any surfaces larger than a few millimeters. So this is one of our tasks, how to make these surfaces fast and efficient, so they can be so this technology can be used even in industry. And we are focusing on 3 main technologies which can make this happen. First is focused on using of diffractive optical elements. When we can, by special diffractive grating, we can, for example, divide the beam into matrix of beams. So basically, we can stamp the whole matrix of beams next to each other, so we can be much faster, even 1,000 times faster. This technology has some advantages. It is quite robust. We can use high laser powers, but it has a fixed design. That means if we want to change anything from the laser source to the pattern itself, we have to buy basically a new diffractive optical element. But with this technology, we have quite nice results. You maybe noticed our world records in this field. Here you can see that we moved from 2.5 years per 1 square meter to just 5 minutes in this case. So quite significant improvement. And another record was connected with the number of beams which we were able to use for simultaneous nanostructuring, and it was more than 40,000 beams at once. So you can imagine it was quite significant improvement compared to a single beam approach. Next technology, which I would like to quickly introduce, is interference patterning. In this case, the input beam is divided to be recombined on a sample to create interference pattern in case of 2 beams or 4 beams. And it has also some advantages. For example, over the previous method, we can change the pattern either by the number of beams, but also by moving this prism up and down, we can easily tune the angle and thus the periodicity of the interference pattern without realigning the setup. But we can also reach much smaller structures below the diffraction limit of common processing optics. So this is also very nice technology. And the last technology which I would like to introduce is dynamic beam shaping using spatial light modulator. In this case, you can imagine it basically like a programmable diffractive optical element. We are calculating computer-generated holograms or phase maps, which are uploaded on a spatial light modulator. And by that, we can change the input beam into almost any shape which we want. In this case, if we use this grating, we are shaping the beam into top hat line, and with this line we scanned over the sample, and again it was a much faster process. Here we have some limitations, basically regarding the LIDT of this element, and that is up to 100 watts or half millijoule at our 1 picosecond pulse duration, which may not seem as much limitation, but our lasers can go much higher. And now finally we can jump into case studies. So as you can guess, our goal is to make these very detailed micro nanostructures on large samples. At least in case of micro machining, this is already a large sample. It was done for a customer which wanted hydrophobic surface to improve heat exchange, and we developed a process which can do this quite fast and efficiently, as you can see. Okay, but that doesn't stop us. We have some records in nanostructuring, but still we are thinking how to make it even faster. Maybe even think about mass production of functional shapes, maybe even complex 3D samples, utilizing some industry process maybe. And we find out that we can do it actually by using our technology to efficiently structure metallic molds. For injection molding, for example, we can transfer the functional structures to plastics directly by standard industry processes, and by that we can induce all the functional properties on the plastics parts itself. We find out that we are able to transfer even sub-micrometer structures from the mold into the plastics, and even combine micro and nanoscale structures on the plastic part. In this case, for example, we tested these plastics part for wettability, and we find out that we are able, by different structures, to tune the contact angle quite significantly. But of course, we are not limited just to plastic parts, but we can structure the metals itself. This case studies just shows that we don't need to use injection molding. In fact, we can structure a plastic part itself. In this case, it's plastics reinforced by carbon fibers. And as you can see, even direct laser structuring is possible down to 1 micrometer in resolution. Again, in this case, for superhydrophobic surfaces. In this case study, we are focused on antibacterial properties. And we find out that there are, again, some structures, in this case on plastics, in this case on metals, which can significantly change the adhesion of bacteria. In this case, we reached 99.8 reduction in adhesion of E. coli, and 92% reduction in case of Staphylococcus aureus. So again, quite significant results, which may have very nice applications in medicine. Another quick look into another case study. In this case, we were focused not on antibacterial properties, but on biocompatibility. And here we introduced structures which can control the cell growth and cell organization, either again by some microstructures, but as well by nanoscale structures. You can see that the cells in this case are elongated in the direction of the structures. So we think that we may maybe mimic some different shapes to even improve biocompatibility even more. But even with these structures, we were able to increase the cell number 5 times on certain structures. So again, very nice result, which improved the biocompatibility of steel in this case. This is just a quick look on production of microfluidic devices. Here we made some custom chips for our colleagues from BioCef. The goal was to observe cell interactions in between the channels, but they were not happy with the chips which were on the market, so we made them some custom shape, custom dimensions, which we can tune according to their needs. In this case, we were working with company Meopta, and the goal was to make efficient process for drilling and cutting of invar, which could be used as a mask during production of OLED displays. And we demonstrated that we can cut and drill invar with 784 beams at once with a green laser. So again, a quite significant improvement. This work was done with Ph.D. and their spin-off PinFlow, which you maybe know from the Neuron prizes from last year. In this case, we structured electrode of their special zinc and airflow battery, and we demonstrated that such structures can improve, in this case, for example, the removal of oxygen bubbles. It's more stable compared to Atalyst, and there are implications that it can improve the overall performance of the battery. We have also quite extensive know-how in structuring of glass. For example, in cooperation with Matfis, we developed technology which can improve the adhesion strength of copper on glass, which is necessary for some advanced electronic microchips. Or we are cooperating with company HolOr, which is producing diffractive elements. In this case, we were testing their diffractive vessel beam objectives, which can reach 2 micrometer in diameter with depth of focus above 2 millimeter. So we were able to structure and cut glass with very tiny diameter. Or we showed that with some sub-wavelength structure, we can tune the reflectivity of glass with nice transparency. And the last case study I would like to show you here is about friction reduction. This was cooperation with ČVUT, and we showed that structures on Altin coating, which was on tool steel, can improve the friction properties. And the black color is here for a reference. All other colors are different laser structures. So again, we show that we can decrease the friction coefficient almost 30%. And compared to standard laser processes, again, we were like 40 times faster. So that was some examples of our case studies and capabilities. And here I have just one slide to show you our brand new workstation, which is just now being installed. In this case, we will have all the technology I mentioned on a single table. So all the multi-beam techniques, but also some common galvo scanners, microscopic objectives, and so on. So it will be a very nice, let's say, test before invest station, where we can even combine all these technologies together and come with some new interesting results. And this question is for you, how we can collaborate. So I showed you our capabilities. So maybe now we have some feelings about some overlaps or how we can, what we can do together. So thank you.
Thank you very much for a fantastic talk. So now the floor is open for discussion. So are there any questions?
Thank you. In the past, we used some metamaterials which were fabricated by laser machining with Thai sapphire laser, which was 100 femtosecond or sub 100 femtosecond laser. So can you compare the processes which go on in your system, which is, I think, 1 picosecond system, and such clearly sub-picosecond system. And also, I did not understand whether you systematically use 515, the second harmonic for cutting, or sometimes the infrared, sometimes the green. You can comment. Thank you.
So first, maybe wavelength. We have option to go from first to second, third, and fourth harmonics. So we can switch it according to the absorption curves of different materials. And regarding the pulse duration, we are talking about 1 picosecond laser system. It is still picosecond, but basically it would be more accurate to say 1000 femtosecond because it is operating in cold ablation as well as 200 or more femtosecond laser systems. So the physics behind the ablation is similar. Yeah. So I believe if you have some results with 100 femto, that we can do the very same with 1 pico. There is not so much difference. Repetition rate, the laser which we have in our laboratory has 50 kilohertz. We can go up to 200 kilohertz in scientific lasers in laboratory, but it's around this value, not higher.
I have a question regarding the principle of antibacterial surface. It is because the bacteria could not attach to the surface because it is highly hydrophobic, or it is another principle?
Yeah, it can be even the wettability which can help with this effect. It can be either super hydrophobic or even hydrophilic surfaces has some effect on bacteria attachment. But I would say the main effect is that the structure has to be smaller than the average bacteria cell size. So then we are decreasing the probability of the attachment. So the bacteria won't start making colonies and eventually die or can be easily washed out of the surface. That's one. And the second is that we can create even sharp structures which can penetrate the bacteria cell, so it can be so-called active surface which can kill it, not just the decrease adhesion.
Other question?
I just wonder that if you maintain the patterning on the surface of the sample by laser, do the core material property change, or it remains same, or it modify?
It is just surface structuring, so
the core
material remains the same.
Okay.
Most of the time.
Yeah. Thank you.
Well, maybe continue on this question, but can you do some surface modification which is not patterning, which modifies by heat the surface layer? Many materials are sensitive to heat, so you can do, there can be phase transformation, whatever, and you can do it selectively. So did you try for something like that?
Not really, because this 1 picosecond pulse duration is basically in a cold ablation regime, which means that the material is in ideal case vaporized before the heat can dissipate into the surroundings. So mostly we are focusing on applications where we want to avoid the heat input into the material. But of course, if we use 40,000 beams at 100 watt laser, then there will be some heat, but it's not the goal. So in case of heat inputs into material, there will be a case of some continual wave lasers and so on.
Yeah, okay. But you have like this shot peening, which is another stuff where you use the mechanical deformation of the surface. It is again not patterning. So do you look at the methods which you have from this perspective, like patterning makes the holes in it, shot peening modifies the microstructure by mechanical means. You can have heat. Do you look at it from this point of view or not?
There are some projects running currently which should combine shot peening and structuring, but so far no significant results from some small preliminary tests.
Yeah, thank you.
Thank you for your presentation. Just a simple question. You mentioned it's just a surface process which you are modifying. So what is the depth or what is the height of the surface which you can modify? It's in micrometers or nanometers just?
Yeah, it depends. The smallest structures presented here were like 200 nanometers deep. It can be a little bit smaller, but not that much. And on the other side, we are drilling through 2 millimeter thick glass. So I would say these are the boundaries basically when we operate.
And basically material doesn't matter.
Material does matter, of course, but with high intensity laser, it's easier because, for example, multiphoton absorption can help to drill glass even at IR wavelength.
But basically metal contacts would be possible to somehow modify.
Yeah.
So, yeah. Thank you.
I wonder about these large area methods you were talking of in the beginning. How do you achieve splitting the laser beam into 40,000 or something like that first? And then I imagine that you need to achieve some precise pattern among these split beams or various beam paths. So what is the precision you are able to achieve in this?
To split the beam, it's not our knowledge. It's the element from HiLASE company. This is a company from Israel which is developing these kind of diffraction gratings. So that's their know-how. And the precision, I don't know what exactly you're asking about, but for example, in the case of 40,000 beams, it was matrix 1 millimeter long, 1 by 1 millimeter, and the spot size was 5 microns. And with all of that, we can scan in this, let's say, 5 micron area for each beam.
Okay, so it's beam splitting essentially, right? By this diffractive element?
Yes.
So you reduce the energy per beam.
Exactly.
But you have so much power that it's not a problem if I understand
that's
correctly.
the point. Yes.
Thank you.
Hello, thank you for the nice presentation. So my question is like, can this technology be implemented for this photovoltaic research? Because you mentioned something about this laser micromachining and surface, like functionalization, surface texturing. But in the photovoltaic technology, we normally need this surface texturing for these tandems, like some solar cell fabrication, any kind of. But the kind of resolution you mentioned is around 1 micrometer, not in the scale of nanometer, if I'm not wrong. So if some comment on this.
Okay, generally it can be used for in case of solar panels and so on. There are many works regarding functional structuring of solar cells. We actually have even some work done, not for solar panels, but to improve absorption of laser light on detectors of laser radiation. And regarding the periodicity with interference patterning and fourth harmonic, we can go with down to 200, 250 nanometer in periodicity. So that's the smallest range on the other side.
And without damaging the surface?
So,
without damaging the surface?
You are removing like 100 nanometers in this case into depth.
Okay.
Tady, looking on these your beautiful videos, you you became expert in this patterning for micro publicity for water, isn't it? Like you have some knowledge maybe what kind of pattern is best for taking the water, for repulsing the water. Do you do some research in that? Or because I can imagine this is very attractive field for application. So
yes,
my question is how much you became expert in this after doing
like this. We have several papers published already on this topic. I believe this topic is basically closed on our side. We feel quite confident.
I'm asking because it just seems to me that with this your technique, it opens new way for this kind of surface modification for hydrophobicity. So if you have new tool, you can design new functions, just like you are showing here with this HiLASE, how it beautifully shows the picture. So is that true or not?
Yes, there are some cooperations now which are using this know-how, for example, for some special kind of microfluidic devices which can move the droplets around to mix it and so on. So that's, for example, application when we are using the superhydrophobicity. But also on this antibacterial samples, we are using modified wettability to improve this effect.
Do you know already which kind of beam or energy or whatever is optimum? Because this is not just like to make a pattern here. I mean, it also depends on what kind of pattern, what is the height of and so on.
Yeah, definitely. But it's nothing unknown in literature. It is quite well described, even with equations and so on, how the structure should look like on different fluids or surfaces and so on.
Did you measure the difference between the artistic glass and just technical glass piece? The different structure.
Yeah, maybe can you rephrase the question?
Technical and artistic glass.
In case of glasses, we were trying some tempered glasses, Gorilla Glass, and glass, and that's it probably.
And what is the structure difference between these types?
Sorry?
How is the structure difference of these glasses?
With different glasses, basically the structure can be the same, but the problem with different glasses is the dents in a glass, how it's made, because it can break easily. Some glass break really easily, but some withstand quite a lot.
And artistic glass didn't?
No, we didn't try this one.
Thanks.
Hello. What is the smallest detail? So spatial resolution of the metal. If you would be to make a regular grid, what's the minimum spacing between
for
lines?
A rectangular grid? Around 250 nanometers.
Okay, thank you. And now, to make the surface hydrophilic, this spacing has to be as shorter as possible, and for hydrophilic and hydrophobic vice versa, or is there this rule?
It cannot be generalized like that. Basically, why it is super hydrophobic is because the water is wetting only the top of micropillars, and there is air trapped in between the structures. So the water is floating on the air below and wetting only top of the microstructures. But it's always an interplay between the material, the liquid chemistry, and the structures itself.
Thank you.
May I ask you if you treat some metallic materials, is there some surface oxidation or changes in the surface chemistry by some, I don't know, selective evaporation of some element and so on? Thank you.
Yes, of course, if we treat metals, there will be some layer of oxides formed during this high temperature treatment, but it can be just a few nanometers up to quite large depths, depends on the process,
just
the exposition time.
Passive layers, let's say, or
yes, that's possible.
Thank you. Maybe a technical precision. If I understood properly, all the energy we send to the surface is used to evaporate the material, and you consider that there is no heat going inside? Or because my idea, is it the same if you are using metals or glass? Because the conductivity is completely different to evacuate the temperature, the heat.
Yes, it depends actually. If we are only on a surface and we can extract the particles, we can be quite confident that not much heat is coming into the material. But if we are making deeper structures, then it's harder to extract the material. It's sitting back into the structure or hole. Then there is enough time for the heat to be dissipated into the interaction zone. So yes, then heat input into material has to be taken into account.
Thank you.
Thank you for the nice talk. My question is, can you modify the pattern? So, for example, instead of regularly distributed dots, to make narrow stripes or something like that?
Yes.
Yes?
Definitely.
Thank you.
Will be my last question, I hope so. So instead of the hydrophobic, what my colleague asks, you can also achieve the hydrophilic, means any type of electrolyte can go in and it will attach, the adhesion will be stronger. Is it? Means have you achieved something hydrophilic nature?
Yes.
The pattern?
Hydrophilic is actually quite more challenging than hydrophobic. It's more about surface chemistry than the structure itself in most cases. But theory says that if the basic material is hydrophilic, then the structure will enhance this effect. So if the base material is hydrophilic, we can make it even more hydrophilic by some structures.
Okay, I don't see any more questions, so I might ask something about the future vision in this technology. It seems to be that you can do a lot of magic, and it's applied in industry. So where it can go? Can you create, for example, something like your 3D setup where you can do three-dimensional fabrication, structuring, sell it to customers in the future, or you aim somewhere else in terms of research?
Well, in terms of research, we are now focused on this brand new micromachining station, which was mentioned on one of the last slides. There will be 5-axis processing system. So we will have to learn how to put basically these 2D processing into some complex forms. So that will be challenging. And our vision is basically to find out some key partner or key application in industry and go more into detail into such process. Because now we are just showing several use cases. We're showing what is possible, but to go more into detail, we need some partner for industry. So that's basically our goal, to find someone like that.
And I've seen you had a lot of partners, so they are more interested after you do the case studies. So do they really use the technology in for making their products, or that's hard?
Yeah, that's hard. But so far, it mostly continues in the form of some projects. So like that.
And what is the biggest challenge? Is it the cost or the time or other parameters?
Maybe both.
Okay, so in the future, if you can make it much faster, much cheaper,
yeah, definitely. Like the cost is always the main factor. If we can do it for free, then everybody would want it.
I see. There is still one more comment.
And continuing on this, you don't aim to get a spin-off to offer this machine to the industry, and so they can find out themselves what they can do with it?
It would be possible, but I would say that this machine is quite huge and multifunctional for industries. So I believe that if we find a key partner, we can build a smaller machine just for the task, not this multifunctional, expensive machine.
Yeah. Well, just continue on this. I understand that this machine is big and it's better if you run it at HiLASE, but do you have companies who come to you and want to make some simple device which will produce only some special products, and only for that this would be typical company desire? So do you have such kind of contacts?
We have companies which are ordering some jobs regularly, and maybe it will come to that soon, but currently we are at a stage that we are looking for such partners.
I'm not really talking about asking to do some job. Well, we had recently some professor from Taiwan, and they produce 3D printers for plastics, and I was really surprised. Like their activity is basically to develop printers and then to sell the printers to the company, and company uses it to make some earrings. Yeah, only earrings, nothing else. But they sell it to the company and maybe other companies. And well, I can see very good prospect in your approach for the same. So my question is whether you have such companies coming to you who would be interested in special laser for one type of processing.
Yeah, basically we are looking for such partners. There were in past some requests, but so far nothing significant.
Okay, thank you very much for nice talk, for the discussion. I thank everyone as well for contributing, and let's thank the speaker again.